This is Mrs. Frobel. In this video, we're going to talk about modern atomic structure. So, up to this point, we've discussed classical structure, and now we're going to actually move into what more of the accepted ideas are. Um, the Bohr model was good, however, it didn't describe molecules or atoms, I should say, that were bigger than hydrogen. And they had to come up with a way to determine the structure of the atom on elements obviously higher than hydrogen. So for the modern theory, they knew that the protons were still located in the nucleus, and they knew that the order of the elements was based on the number of protons within that element. They were still struggling to try to figure out electrons, and we'll talk a little bit later about where those electrons are actually located. Now, probably the most important thing is that we do know that electrons are very random. They aren't necessarily stuck in place. The best analogy I give to my students is if you imagine housefly trapped in a bottle. They're essentially zipping and zigging and zagging all over the place. So they're constantly in motion and they don't stay in place for very long. Now through the Rutherford experiment and investigations from other scientists, they found that most of the volume is found outside of the nucleus. Okay, so what happened is scientists actually came up with a way to measure the mass of a single atom. Up to this point, they were just measuring a group of atoms, but eventually they got to the point where they could be very precise about things. And they noticed that the mass of the hydrogen atom was 1.674 times 10 to the negative 24 grams. Now, the interesting thing is they were able to determine the mass of the proton thanks to people like Moseley, and eventually they were able to determine the mass of the electron. Now notice that the mass of the electron is 10 to the 28th, so it's significantly smaller than the proton. Remember, when you're talking about negative exponents, the bigger the number, the smaller the amount. So the fact that the electron is significantly smaller shows you that here we have 1836 divided by 1837. So the mass of the proton is taking up a huge chunk of the atom. The question is, what about the electron? We're talking about a tiny, tiny fraction of the overall mass of hydrogen. So if you look, most of the mass is primarily in the nucleus. But the interesting thing is a lot of the action occurs with the electron. And you're going to find when we talk about bonding, we're going to sometimes just ignore the nucleus and just pay attention to the electrons. But when we're looking at the elements and the way we arrange them, we're really arranging them according to the number of protons within the nucleus. Okay, so they came up with a more precise method of measuring atoms by themselves. And as a result of this, they came up with a measurement of a new type of hydrogen. And this was just bizarre to them. They thought, Dalton had said that for all elements, there has to be the same type of atom for each element. So this was amazing to them. They thought, how could this be? And the weird thing is, only 0.015% of the hydrogen was this new form of hydrogen. Now, the interesting thing is it was twice as heavy as the regular form of hydrogen. And since it was heavier, they called it heavy hydrogen for a long time. Okay, so for heavy hydrogen, we know the atomic number of hydrogen is 1. For heavy hydrogen, what do you think it is? It also is 1. Okay, for the atomic mass of hydrogen, it's 1.0079. And if you had to guess, how many protons would there be for regular hydrogen? Hopefully you said 1, and we're assuming a neutral atom, so we're going to say 1 electron. Well, this heavy hydrogen, they found it to be 2.0141. And if you had to say the number of protons, what would you say? Yes, it would be 1, and it's a neutral atom, so it has to be 1. So the question is, why was this hydrogen so heavy? The mass wasn't coming from the proton. The mass wasn't coming from the electron. So they had to come up with an explanation for this. Well, along comes a man by the name of Chadwick. So Chadwick, the interesting thing that he found is that he discovered a new particle. So the presence of protons wasn't enough, the presence of electrons wasn't enough. So he essentially came up with a mass, and notice it's 1.675 times 10 to the negative 24th, so it's definitely bigger than an electron, but the question is it bigger or smaller than a proton? It's the same. So he found that it had the same mass, it had 0 charge, and because it was 0 charge, he called it a neutron. Okay, so guess what? Dalton's theory of atomic structure had to be revised. So they discovered, because of the presence of a proton, there was an extra particle called a neutron. So what does this mean? Well, they had to come up with something which they call a mass number. Now, when we talk about radioactive elements, mass number is really going to be important because it's essentially the summation of protons and neutrons together. So when we're looking at a mass number of a specific element, we're looking at how many protons and neutrons combined equal that mass. So this means that isotopes, and this is something that they finally realized with the presence of heavy hydrogen, it has the same number of protons. But guess what? There's this additional additional particle called a neutron, which will cause it to have a different mass number. So a lot of the radioactive elements that you're familiar with, they have a specific mass number based on the number of neutrons that are added to the nucleus. So please remember, with isotopes, they will always have the same number of protons, therefore their atomic number will be the same. However, the mass number will always be different. Okay, here I have a nice long table here, and I just want to point out for hydrogen, so notice that they all have the same atomic number. However, their mass number is different. So we have 1, we have 2, and then we have 3. Now, notice that for each one, it has the same number of protons. And because it is a neutral atom, it has to have the same number of electrons. However, guess what? Hydrogen 1 does not have the presence of a neutron. You'll see this question again on a quiz or a test. Hydrogen 1, mass number 1, does not have the presence of a neutron. However, hydrogen 2, which is called deuterium, that probably sounds familiar, notice it has 1 neutron. And then tritium, which is mass number 3, has 2 neutrons. We go to the next series of okay, I'm going to do helium and oxygen, and I'll let you do the others. Okay, so the mass number for helium we know is 2. I'm sorry, the atomic number is 2. The mass number, so wherever you see the dash after the element symbol, oh, sorry, I made a boo-boo there. I'm just going to cross that out and make it a 4. My eraser doesn't work. Okay, so we have a mass number of 3, a mass number of 4. For the number of protons, they have to equal the mass number, so both of these have 2. They are neutral atoms, so they have to have an electron equal to them. Now for the number of neutrons, notice that we have a mass number of 2, but we have atomic number, mass number of 3, atomic number of 2. So we're going to subtract and we get 1 neutron, and then 4, mass number with 2 atomic number, subtract and you get a number of 2 for the neutron. So it's always the mass number minus the atomic number to tell you the number of neutrons. Okay, so for oxygen, these are all 8s. And for the mass number, I'm just going to write the number that's after the element symbol, so 16, 17, and 18. And then the number of protons, I just use the same atomic number. And the electrons, it's a neutral atom, so I'm going to put 8 again. And then for number of neutrons, I'm just going to subtract. 16 minus 8 is 8. 17 minus 8 is 9. And then 18 minus 8 is 10. So what I want you to do is, on your own, I want you to do chlorine and uranium. So you want to look up their atomic numbers, and then the mass number is listed right after the element symbol, and then you should be able to figure out the rest. For now, just go ahead and skip nuclear charge because we don't want to discuss that yet. Okay, so before Dalton's time, or I should say around Dalton's time, he arbitrarily assigned hydrogen a mass of 1. And what that did is it actually made carbon-12 less than 12. So when they were getting into more specific masses, oxygen was set at 16, but there were discrepancies with the other elements. So they had to come up with a compromise, and what they decided is carbon is somewhere between hydrogen and oxygen, and if you make everything relative to 12, so hydrogen actually stays as 1, it's a little bit more than 1, and the amazing thing is oxygen actually stays pretty close to 16. So it was kind of like a compromise. They decided to base the periodic table on carbon-12. So that means carbon mass number 12, and you're going to find that there's other isotopes for carbon too. So if anything, it's important to remember that the atomic masses of the whole periodic table are based on carbon-12. So we're assuming carbon-12 has the exact mass of 12.00000. Okay? So everything is relative to carbon-12. So what does this do? Well, we actually have atomic masses, and I'm going to do a calculation here before I do it. So what I'm going to do is, just to let you know, I'll do the calculator in a minute. So I'm going to take 99.985% and I'm going to multiply it by this mass, and then to that I'm going to add a separate calculation of 0.015% times the mass of hydrogen. So let me get my calculator up here. Okay, here we go. Sorry, I lost my number there. Oh, here, I'll just select this again. I apologize. I just want to show you how you do the calculation because guess what? You're going to do it yourself. Okay, so I'm going to take 0.99985 times 1.007825. Okay, and I get 1.00767. Sorry, I don't know why I did that. I gotta go back to it. And to that, I'm going to add, and you want to use parentheses. I gotta go back to that slide. Okay, so to that parentheses, I want to add 0.00015 times 2.01410. And notice I'm using parentheses around this second equation. Okay, I've essentially calculated what you see at the bottom here, 1.00797 AMU. Okay, that's how you calculate the atomic mass that you see on the periodic table. So you take the percentage of each isotope and you add their averages together to give you an average atomic mass. So this is something that's automatically done for you, but you kind of have to learn how to do it so you know where they got it from. Okay, so I'm going to do a couple instances here. So here we have chlorine 35 and then chlorine 37, and we're going to take 0.7553 times 34.96885, and to that we're going to add a second calculation of 0.2447 times 36.965 and 90. Okay, so we're going to do that together and see what the atomic mass is. Okay, so I apologize. I don't know why it keeps flipping there. Okay, so I'm going to clear this out. Okay, so I'm going to use parentheses around each equation here. So 0.7553 times 34.96885, close parentheses, plus another parentheses, 0.2447 times 36.96590. Okay, and then when I add them together, so my average atomic mass is 35.24. I would just go 4 place units. Okay, so 35.24. All right. Okay, so this essentially is 35.24, and hopefully when you look on the periodic table, you have something very close to that. Okay, I'm going to have you do this last one here, okay? So don't be surprised if you see this on the video assessment.